This week's lecture will go over how statistics can be used for description and inference. Also, we'll discuss the concept of statistical significance in defining the results of a study and describe the interrelationship among type 1 and type 2 errors and statistical power. Further, we'll explain the advantages and disadvantages of different sampling techniques and describe common measures of central tendency and variability. And lastly, we'll differentiate between appropriate uses of parametric and non-parametric statistical tests. Statistics are tools that can bring some sort of order to irregular-looking datasets, which allows for comparison between groups and makes conclusions based on the results. So this is why statistics is an essential component of research, because if not, how can you see that this drug improves health or not? A thing with statistics is that it connects with the research design. There are certain statistical tests that need to be used depending on what you are looking at. You just can't run any statistical test to the data. It has to make sense. So, there are different software packages that you can use to help make sense of the data you just collected. This does all the calculating for you rather than doing it by hand, which is kind of old school. Some software packages that, can do this is JASP, R, and SPSS, and even Microsoft Excel can do some statistics. However, the most popular package is SPSS. One thing is that if your study design is complex, basic statistical tests may not be enough and require a little bit more sophisticated tests to help answer your question. So you might need to consult with a statistician who is more experienced and more knowledge in that area. Nonetheless, it is important to have a working knowledge of basic statistics for being able to communicate with statisticians and understanding the research process and interpreting the results. Statistics is a subfield of mathematics that deals with procedures for collecting, analyzing, interpreting, and presenting data. Statistics is used for two general purposes: description and inference. Descriptive statistics can provide indicators of central tendency and variability of the variables of interest. Or really, it gives you different ways of looking at representative times for the whole group. Inferential statistics is a mathematical approach to deducing the probability of the occurrence of a characteristic in a population based on the measured characteristics of a sample. So generally speaking, this can give you insight into how well some score is for a certain population that have the same characteristics that were measured in the study. Descriptive statistics are used to characterize a group with regard to a set of measurements or data taken on all members of the group. Descriptive statistics include central tendency, which is the extent to which values cluster in a data distribution plot, and variability, which is the extent to which values are spread out in a data distribution plot. Both are important for characterizing the distribution of a data set. A measure of central tendency is the one numeric value that represents the entire data set. One thing, though, is the choice of that measure of central tendency may be calculated differently depending on the context. So I'm sure this is all familiar with you with the mean, median, and mode. Again, the mean is the arithmetic average of a group of numbers, calculated as the sum of all the numbers divided by the total number of values in the data set. For example, we can get the mean average score for a certain quiz taken out of you throughout the semester. The median is always a datum or a single data value that resides in the middle of the data distribution, such that half the scores fall above it and half below it. The last and least precise indicator of central tendency is mode, and it is the most frequent score in the distribution. Remember that the mode is different from both the median and the mean. And one thing is that if there are two scores occurring with the same frequency higher than the frequency of all other scores, the distribution is termed bimodal. Measures of variability provide an indication of the distribution of the measures within a data set. So depending on the nature of the data collection, the scores might clump toward one end of the data distribution, the middle, or evenly distributed. The range is the difference between the high score and the low score, which is fairly straightforward. Another indicator of variability is the standard deviation. This is an estimate of the spread of scores away from the mean. Also, this is probably the most commonly used indicator of the variability of a research data set. The last one is the standard area of the mean, which is the estimate of the expected difference between the sample mean and the population mean. Some things to consider is that when the standard deviation gets smaller, the standard error of the mean gets smaller as well. If the sample size gets larger, the standard error of mean gets smaller. So having a smaller number is preferred, as it gives a more confidence that your sample mean is an accurate representation of the population mean. When reading research papers that involve human participants, it is common to use means and standard deviations for age, height, and weight. I'm sure you noticed when reading the research articles for the assignments that you notice that these variables have the mean and standard deviations. You'll also see these descriptive statistics in other variables such as strength measurements, number of repetitions, and possibly nutrition intake of a certain macronutrient, for example. When we look at inferential statistics, they are used when the goal is to take data or measures of certain characteristics from a research study and from these make generalizations or inferences about the same characteristics of a larger group. There are generally two types of questions that can be answered when using statistics for purposes of inference. One, is there a relationship between variables? And two, is there a difference across conditions? One important use of inferential statistics is determining whether a relationship exists between two or more variables of interest within the population. One example is there a relationship between GRE scores and successful performance in a particular graduate program? So knowing this can be a screening tool for predicting which students will and will not be successful in the program. Another example is there a relationship between a simple field test and difficult laboratory-based tests for a variable of interest? So we have our gold standard of determining VO2 max in the lab through the metabolic cart, but can the scores from a field-based test such as the Cooper 1.5 mile run demonstrate a relationship with the laboratory setting? And the answer is yes. They have established a relationship, which is why we may use that test, such as the Cooper 1.5 mile run test, to get an estimate of an individual's VO2 max if the metabolic cart is unavailable, or if you're at a setting where they don't have that particular equipment. The second general question answered by inferential use of statistics is whether true differences exist between conditions, such as are there differences between males and females, the young versus the elderly, or trained and untrained on some sort of variable. Another common research question is whether there are differences before and after an intervention or some sort of treatment. This is usually a pre to post measurement and is often used looking at diet interventions, following some sort of training program, a drug, and also you can test against with another treatment, such as comparing two diets to each other. Each statistical test for a relationship or difference is founded upon a hypothesis or prediction about the outcome of the test. We discussed what a research hypothesis is previously, but just to reiterate, a research hypothesis is a statement indicating the researcher's true expectations as to the outcome of the study. This may be the same as or opposite of the null hypothesis. Statistical tests are conducted to test statistical hypotheses. These statistical hypotheses can take two forms, null and directional. A null hypothesis is a statement indicating expectation of no relationship or no differences for purposes of statistical testing. For example, there will be no differences in deadlift strength before and after an 8-week training protocol. The difference between a research and null hypothesis is that a research hypothesis is based on a logical assumption based on previous literature. A directional hypothesis is a statement indicating an expected direction of a relationship or a difference for purposes of statistical testing. Since it's easier to test using statistical procedures, it is usually the null hypothesis that is tested. A question that remains is what degree of correlation or amount of difference is necessary in order for there to be support for a hypothesis. This is where probability comes in, and this goes back to the most common example of flipping a coin and having it come up heads is 50%. So out of 100 coin tosses, 50 of those should come up as heads. However, because of error due to chance, there may be more or fewer than 50 with the coin heads up. In this case, the results were different from those predicted. Researchers make a decision as to what amount of error due to chance they are willing to accept, which is always done before the study. This level of tolerable error due to chance is known as the alpha level, and this alpha level is also referred to as the level of significance. The alpha level most commonly selected in studies is alpha equals to 0.05, or a 5% level of confidence, which indicates that the odds of the study results being an error due to chance are 5 in 100. There may be some cases where the alpha level is set at 0.01 or 0.001. This may be used for a drug study where we wouldn't be comfortable of a result of 5 deaths for every 100 participants. The alpha level is set before the study is conducted, but what is reported after the study is the probability associated with the likelihood of the results erroneously being due to chance. This is often referred to as the p-value in a research paper. The statistical package will provide you with this p-value. So when a p-value is smaller than the alpha level, the null hypothesis is rejected and the results show a significant relationship or significant difference. However, when a p-value is greater than the alpha level, the null hypothesis is accepted and the results are not significant. Some researchers out there will try and make a case for the results of a study with a p-value equal to 0.06, where they'll state, as close to significance or trending to significance. However, though, in statistics, you cannot make the case for significance with this value. For it to be significant, the p-value always has to be less than the alpha level. Sometimes there is an error due to chance that occurs in the results of a research study. A type 1 error is where the results are significant when there is really not a significant relationship or difference in the population. A type 2 error is where the results are non-significant, but really there is a significant relationship or difference in the population. We'll often use the truth table to indicate the potentially correct and incorrect decisions as it relates to accepting and rejecting the null hypothesis. We can see that alpha is the probability of making a type 1 error, while the probability of making a type 2 error is labeled as beta. We've discussed this test previously, but again, this is another test for the meaningfulness of the results of a study evaluating differences. This is a practical value for the measured difference that results from application of the treatment. So for example, the results of the training program resulting in a 10% change in the variable being measured has an effect size of 10%. We can calculate the effect size as long as we have the mean score and the standard deviation. So again, an effect size of 0.2 is small, 0.5 is moderate, and 0.8 is large. In clinical fields such as athletic training and physical therapy, some researchers will discuss the findings as clinical relevance or clinical importance. This is usually when the results of the study are not statistically significant, but the researchers attempt to make a case for the effect size being large enough that it is likely to be of interest or of importance in clinical practice. Furthermore, since there is no objective test for the term clinical relevance, the researchers try and make the case with logic along with knowledge of the clinical situation. The thing that is important in research is finding the participants to help answer your research question. The participants in the research study are referred to as a sample for the study and are selected as being representative of the larger population of individuals, so the results can be generalized. The population can have defined characteristics such as obese individuals with type 2 diabetes or untrained individuals. Just remember that the results will only be generalized to that population and cannot be generalized to another group. Using research terminology, a statistic is a value representing a characteristic of a sample, and a parameter is a value representing a characteristic of a population. Something that occurs early in the research process when designing a study is determining how many participants are needed to help answer your research question. In general, you want a large enough group to be representative of the population, so not too little or too much. You will need to find the right amount to not only answer your research question, but also the practical portion of it, such as the time it takes to collect the data, the amount of supplies you have, the availability of testing apparatuses, etc. A software that we can utilize or calculate to determine how many participants we need is power. So power is the probability of correctly rejecting or accepting the null hypothesis. So really, we are trying to avoid type 1 and type 2 errors. The greater the power of a study, the greater the odds of arriving at statistically significant findings that accurately reflect the population. And usually power is calculated at a level of 0.8. Depending on your study design, you will need to calculate an acceptable level of power. However, this may vary depending on certain information. The information you may need to include is your predetermined levels of alpha and beta, an indication of the variability of the measures of interest, and identification of the size of the relationship or difference in the conditions that you consider to be meaningful. In general, the smaller the effect size between conditions and greater variability of measures of the interested variable, the larger the sample size is needed. Another component of the research process, and before conducting a research study, is determining where will the participants come from. There are some different approaches for selecting the sample. One is random, where all members of the population have an equal chance of being selected. So with a sample that is adequate, the sample should also be accurately representative of the population. However, it is important to recognize that sampling does not guarantee representative of the population, and that there's always the possibility of sampling error in which participants in the study don't represent the population. Another method is stratified random sampling, which all members of designated subgroups of the population have an equal chance of being selected. So, for example, the income of varying populations. If an extremely large sample is needed or an unwieldy population, a systematic sampling method may be utilized. This is selecting every nth individual on a list. So you can say every 20 individuals be selected, or every 20th individual will be selected. The last method is convenience sampling. This is selecting qualified, readily available participants. So if you want to study energy expenditure in children in the United States, it would be impossible to get participants from all over the country for your study. So instead, you'll be looking at a more local area that is a little bit more convenient on collecting the data. A thing with convenience sampling is that you need to set inclusion criteria so that the sample may be representative of the larger population. Inclusion criteria is setting certain characteristics that individuals must possess to qualify for participation in a research study. So, for example, some studies require participants to be resistance training at least 2 times per week for at least the past 3 months on a certain muscle group. Moreover, there's also exclusion criteria. This is setting certain characteristics that individuals must not possess to qualify for participation in a research study. One example of exclusion criteria is having a BMI greater than 30. The reason is that certain measurements, such as an ultrasound measure of muscle thickness, has a limit on what it can measure. So if the person has a BMI greater than 30, then you may not get all the muscle of that participant. Random assignment is different compared to random selection. If you have 3 groups in your study and all the participants have similar characteristics at the beginning of the study, it is important to randomly assign the participants to one of those groups. This is to have good internal validity for the study. If you had the participants choose their group, then your internal validity isn't as strong anymore. Before a statistical method is chosen to analyze a dataset, it's important to know the type of the data collected, since there are certain methods that are only for certain types of data. Nominal data does not have any numerical value and are labeled by name or category. This also usually involves sorting data into a category and doing a frequency count of the number of data in each category. Epidemiology is a good example on using nominal data. Ordinal data is ranked numerical measure. This provides more information than nominal data because they are ranked. Another data level is interval data. This is numerical measures of quantities for which 0 does not indicate complete absence of the quantity. The example that always is used is with temperature. So a 0-degree temperature does not mean an absence of temperature, but only a very cold temperature. So you cannot say that 10 degrees is half of 20 degrees since the temperature can go into the negatives. The last data level is ratio, where numerical quantities for which 0 indicates the complete absence of the quantity. So this is where 0 is an absence of the quantity being measured. Some examples of this are age, height, weight, and distance. All statistical tests fall into either parametric or non-parametric. Parametric is a category of statistical tests used for sets of interval and ratio data that meet certain assumptions related to distribution. For a parametric test to be appropriate for a dataset, it has to be either ratio or interval and must meet certain assumptions. One assumption is that the variable of interest must be normally distributed within the population. Second, the variable of interest must have the same variance within samples drawn from the population. And third, scores or measures for the variable of interest must be independent. Non-parametric tests are used for nominal and ordinal data, as well as for interval and ratio data that do not meet the assumptions related to distribution listed on the previous slide. So a way to determine if a set of ratio or interval data do or do not meet the assumptions for parametric testing is from estimates of skewness and kurtosis. Skewness is the highest frequencies of scores that do not fall centrally, but are shifted to the right or the left, while kurtosis is a vertical shift in the normal curve such that the middle of the curve is either elevated or it's depressed. Both of these terms are a variation to the normal curve, which you can see on the right. A normal curve is a frequency plot of what is termed a perfectly normal distribution of scores. You can see that the curve is bell-shaped and horizontally symmetrical, and that the mean, median, and mode is the same point in the center of the distribution curve. Also, the area under the normal curve includes 68% of scores within one standard deviation, 95% of scores within 2 standard deviations, and 99% of scores within 3 standard deviations of the mean. The figure on the right shows us a positive and negative skewness where the highest frequencies of scores do not fall centrally, but are shifted to one side or the other. So a curve with positive skewness is also termed right-skewed, right-tailed, or skewed to the right, while a curve with a negative skewness can be termed left-skewed, left-tailed, or skewed to the left. So the last thing is showing you a figure of a curve displaying kurtosis. So this might arise when there are more or fewer average performers being tested. So a higher peak represents a larger value for the standard deviation, and a flatter peak represents a smaller standard deviation. Some things that need to be completed by Monday, November 9th by 11:59 p.m. is completing Quiz 9 and also submitting means and standard deviation assignment. Again, please submit as a Word document or PDF file, and also do not submit any pictures or screenshots of the assignment.